In this part, we're going to learn about exponential distribution. Also, it's a widely used distribution for one reason is that in real life, some variables that we are interested in, they exhibit a probability distribution that you will learn that we call that an exponential distribution. So what's an exponential probability distribution? Its PDF looks like that. It's equal to lambda e minus lambda x. So what's lambda? Lambda is called the parameter of the distribution. Remember, for the normal distribution, we said that when we say that x is normally distributed, I will ask you give me the two parameters, which are the mean and standard deviation. When you tell me that y is exponentially distributed, I will tell you, all right, so what's its parameter? You will tell me you give me its lambda. So what is lambda? Lambda, in fact, it's the inverse of the mean of the values of that variable. Okay, and in an exponential distribution, what's very important or what's very specific about it is that the mean is equal to the standard deviation. Okay, and these two are equal to the inverse of lambda, which is the parameter of this distribution. So how does it look like? We've seen in the normal distribution, the PDF looks like a bell-shaped. So how does a PDF of an exponential distribution look like? In fact, all what you need is to know the value of lambda, the parameter of the distribution. Okay, so for example, for lambda is 1, this is how the PDF will look like. And this is why it's called the exponential distribution, because it starts high, okay, at the beginning, at the smaller values of the x or whatever this variable, and it decreases exponentially, meaning that quickly, not like linear. It's not, it does not go like that, okay, it's exponential. And look what happens to this curve when with different values of lambda. For example, for lambda is 0.5. Okay, it's like that. The exponential part is less, okay, while for a larger lambda like 2, look at how exponential it's going to be. So you can see the huge decrease in f of x when x goes from 0 to 1, and look how this decrease is much at a less rate when you go between 1 and 2, and then between 2 and 3. It's almost not changing anymore when x reaches a higher values. Okay, this is only for your information, because in real life, when you're observing a certain variable and you plot its histogram, then if you can see something like that, okay, where we have very long rectangles on only at the smaller values of this x, and these rectangles get much less at the higher values, then you say that I think I have an exponentially distributed variable. So because the PDF of the exponential distribution is a very simple form, it's not like the normal distribution, then here we really do not need to refer to any table, but the probability statements are pretty simple, right? These will be given to you, so you can use them to answer any question. The probability that x is greater than a specific value, so it's an upper range of a specific value of x. This is given as e to the power minus lambda x. Remember, lambda is the parameter, so it's a given for you. And p of x less or equal than x, as expected, this is the complement of the first one, right? P of x less, while on the top it was greater. So this is 1 minus e minus lambda x. And also, we are given that if we are interested to see what the probability that x is between two specific values, x1 and x2, this is how you get it. So it's e minus lambda x1, where x1 is the smaller, okay, of the two. It's x1, the smaller, minus e minus lambda x2. Okay, keep these handy for yourself. Whenever you have a problem about exponential distribution, you can use these to answer the probability questions. So let's have an application about exponential distribution. We're given here that we're talking about the lifetime of alkaline battery. So we are given that it follows an exponential distribution and the parameter is 0.05. And we are told that the lifetime is measured in hours. And then we have to answer 3 questions here. Okay, so first, remember to always define your variable. What's my variable? So let's call X, okay, the lifetime of an alkaline battery. And this is in hours. So that we can interpret the results in this from this perspective. Okay, what do we know about that? We know that the lambda is 0.05, so we can answer the first question. The question was, what's the mean and standard deviation? As we learned in the previous slide, the mean is equal to the standard deviation when it's exponentially distributed, and these are equal to the inverse of your parameter lambda. So that's equal to 1 over 0.05, so that's 20. And 20, of course, hours. Why? Because X is in hours, so of course the average will be in hours. All right, part B, find the probability that a battery will last between 10 and 15 hours. So in probability statement, this is, we remember the third probability that we learned, or that give us the answer, where x1 is 10 in our case, x2 is 15, so I can show that now in these specific values, and equal to, this is lambda, and this is x1, this is lambda, this is x2, right? All what I'm doing, I'm plugging the figures there, and let me give you the answers for each component so that you can practice it on your own and verify your answers. So this is, the first one is 0.6065, second one is 0.4724, and then the probability will be 13.42%. Okay, that the battery will last between 10 and 15 hours. Now, part C, what the probability that a battery will last for more than 20 hours. More than 20 hours, that means X is greater than a certain X, where X is 20. So also I'm going to simply apply the equation that was given to us, equal E minus lambda X, where X is 20, right? So the probability is 36.79%. Okay, I hope that was easy. In fact, the problems related to exponential distribution are very straightforward. Another example to practice the exponential distribution, it's example 8.8. So here we are talking about a checkout counter. The process is exponentially distributed. Or in fact, it's the time of the process, okay? And we have a service rate of 6 per hour, all right? And we want to answer the following questions. First, again, let's define very well our variable. Here we know that the variable is the checkout service time, which I want to represent it in minutes. Why I thought about minutes here? Because I looked at the questions and all the questions are in minutes. So that's why I thought, let me define X in minutes. It's up to you. You can define it as hour, but then you have to do something a little bit different than what I'm doing. All right. We are given this service rate of 6 per hour. What's that? Okay, this is lambda. How? How did I know that this is lambda? We know that lambda is the average of the mean. And the mean is what? It's the average of times, right? So I know that lambda is the inverse of the mean. And lambda, or if you look at this rate given to us, it's 6 customers per hour. We call that a rate, not a time. And a rate is nothing but the inverse of a time. So what are we saying here? 6 customers per hour. That means in 1 hour I can serve 6 customers, right? This is what the difference between a time and a rate, while the variable itself was in minutes. It's simple time. Okay, now because all the questions are in minutes and I have lambda given per hour, and I know that in my equations of the exponential distribution, we have e to the power minus lambda times x. So I'm multiplying lambda, which is per hour, by x, which is per minute, which is in minutes. I cannot do that. I have to convert one of them. I prefer to convert the hour into minutes so that I do it only once, because all the three questions are in minutes. So I will convert that. We are given that lambda is 6 customers per hour. So to convert it, you multiply. I want to get rid of this hour, right? So I multiply hour by 60 minutes, right? So it's like multiplying by 1, because 1 hour is 60 minutes. But this will allow me then to get rid of this hour. So hour, and what will be left is customers and minutes. And I have 6 over 60. So this is 1 customer per 10, right? 6 and 6 will cancel. I will have left 10 in the denominator. So it's 1 customer per 10 minutes. So this is 0.1 customer per minute. Now the time unit of my lambda complies with the time unit of my x. Now I can proceed. So part A, what the probability that x is less than 5. So I will use the first equation, p of x less or equal than 5. So it's 1 minus e minus 0.1, which is my lambda, now expressed in customer per minute, and I multiply it by 5. You see, this is what I was referring to, that otherwise I could not have multiplied this lambda by the x, because before I do the conversion, they had different time units, and I'm not allowed to do this. Okay. Second question. What's the customer leaves the checkout counter more than 10 minutes. Okay, so this is p of x greater than x, where x is 10. So I use this equation, and I get 36.79%. And finally, what's the probability that the service time will take between 5 and 8 minutes? So I refer to the third equation, and I plug everything in place, and I get 15.72%. Okay, so pretty much very straightforward. All what you have to do is to know what to plug and where. In this example, we had to do the conversion for the lambda, okay, from customer per hour to customer per minute. Otherwise, I could not have multiplied these lambdas by the x's, right? Because they had different time units.